All right, good afternoon. Um, just a quick discussion about what we did yesterday. We've been dealing with the vertex form of a quadratic function for a little while, about a day and a half, and then yesterday what we did was we started talking about the vertex form of a function. But we were more interested yesterday in features of the graph that cannot be found by looking at A, P, and Q. So things like x-intercepts or y-intercepts, that's what we were concerned with yesterday. And the main idea for finding x and y-intercepts was that to find an x-intercept, you let y equal 0. To find a y-intercept, you let x equal 0. That's really what it boiled down to. Today what we're going to do is start looking at a different form of a quadratic function and then start doing some problem solving with quadratic functions. All right, so we have what's called a parabolic mirror. Parabolic mirrors have the same shape as a satellite dish, and what makes them unique is that when things reflect off of the mirrors, they reflect to a common point called the focus. So parabolic mirrors focus beams of microwave radiation if it's a satellite dish. So on a satellite dish, you have that parabola, that metal parabola, that the microwaves from the satellite, actually microwaves are hitting that parabola and they're reflecting and they bounce off to a particular point. That's where that arm is sitting. If you've ever looked at a satellite dish, there's an arm out in front. It's got that sensor on it. That's where all of the information goes. Gets, through magic, turns into a picture on your television. Okay. This happens to be a mirror. And there's the cross section of it. It says, how would the quadratic function be different if the outer image were considered the origin? Okay, so I'm going to actually go through A first, even though you asked about B. So we have this at the origin right now in question A. So the quadratic function is A times x minus p quantity squared plus q. And since P is 0 and Q is 0 when the vertex is at the origin for question A, that's what the function becomes. This point here has a y coordinate of 30 because it's 30 centimeters tall, and it also happens to have an x coordinate of 30 because 30 is half of 60. So if you want to find the value of A, which is the missing parameter, then you load in x comma y. So we're going to have 30 equals A times 30 squared. So A will be equal to the 30 on the left divided by 30 squared, and that's going to give you 1 over 30. So the equation of because 30 over 30 squared is 30 over 900, which is 1 over 30. The equation in A is 1/30th of x squared. Now, I mentioned yesterday when we did that arch problem that it didn't matter where you put the origin, you have to get the same value for A. Because it has the same shape no matter what, right? It doesn't matter where we put the origin, the shape is what A defines. So that means in question B, we still have to have 1 over 30. Now I'm going to show you how to prove it has 1/30th as a value in a second. But now it's saying, what if in B, now I got to read it again, what if the outer edge were considered the origin? So what I'm going to imagine they mean, McKenna, is this. What if that were the origin? I mean, outer edge is a little arbitrary because they could mean the outer edge on the left or the right. But I'm going to use that. Now, if that's the case, then the vertex will be at negative 30, comma, negative 30, won't it? Because the vertex will be 30 to the left of the origin and it will be 30 below because it's a depth of 30. So we are then going to have x minus p, which is negative 1/30th, negative 30, and then squared minus q. Well, plus q, but q is negative. So that's the equation. Now, what if you didn't recognize that since the shape is determined by A, they have to have the same A? If you didn't realize that, then you would need to find a missing parameter, wouldn't you? And that would mean you would go to your graph and you would put in an ordered pair. We've learned you can't put in the vertex. But I can put in the origin here. The origin is a point on the graph. I'm going to put 0, 0 here. 0 for y, 0 for x. At this point in time, do any of you recognize you were going to get the same value of a? To simplify it a bit, if I move the 30 over, now it becomes patently clear that you're going to get the same value of a. So you could have done it by a missing parameter, or you could have done it by saying, well, man, a has to be the same no matter where the parabola is. Any other questions anybody would like me to go over? All right, we are going to move on now to what's called the standard form of a quadratic function. So you'll need your note package open to this lesson. Unfortunately, I didn't write the page down, but you can find the page quite easily. Page 10. So what we're going to be doing today is analyzing quadratic functions when they are in standard form, not vertex form. And at the end of this lesson, you're going to have some practice problems to work on for Monday's class, to be ready for Monday's class. And I will also hand back your exams so you can take a look at them. Final reminder here, if you did not write your unit exam yet, you'll be writing it Tuesday after school. You need to make arrangements to make that work, please. You'll be writing a different exam than the one that we wrote on whatever day that was, Wednesday? Doesn't matter. I just want to be able to give back the exam so people can look at them and not have to wait a whole week. We're also going to today, instead of analyzing quadratic functions, we're going to analyze in standard form. We're also going to analyze quadratic functions in situations where we create the quadratic functions. We make them up. That sounds like we're just randomly making up quadratic functions. That's not what I mean. Warm up. Simplify. What does simplify mean in this context? It means multiply it out. If I want you to go get 12 donuts from Tim Hortons, I don't say go get 3 times 4 donuts. 3 times 4 is not as simple as saying 12. So generally speaking, simplify means to expand. Now I want to talk for a second, just as a detour, about x minus 5 quantity squared. And boy, the semesters bleed into the semesters, especially with all this COVID stuff. I can't remember if we've had this conversation or not. But boy, if I ask you to simplify x minus 5 quantity squared, and you want to see the vein in my forehead start bulging and throbbing, go ahead and write down x squared plus 25 and see what happens. See what my reaction is. I start twitching. I think, oh my goodness, we failed you. Somewhere along the line, we failed you in mathematics. And some of you might go, oh, well, that's because it should be x squared minus 25. That almost makes me twitch even more. This is x squared minus 10x plus 25. Because when you are asked to square a binomial, that means you are asked to take that binomial and multiply it by itself. And you know what? All joking aside, I'm joking about it, upsetting me. I don't get upset over things like that. I view it as an opportunity to fix the mistake. All joking aside, if you haven't been doing that, we need to get that cleaned up. We need to fix that mistake because you can't afford to make this grade 8-9 mistake at this level. You'll get the math wrong, even though you understand the principles. So I would FOIL this out and have x squared minus 5x minus 5x plus 25. One final comment here. The level of writing that you put, it depends on you. Many of you will go from x minus 5 squared to x squared minus 10x plus 25. No problem. Some of you need to write it down like this to see it, and then write x squared minus 10x plus 25. Some of you might need to write it down and FOIL it out. Okay, but you need to be right. This is the most important thing. I don't care about the work here. I need the answer. So when you simplify this, we're going to have negative 3. I'm just going to rewrite it times x minus 5 squared plus 7, which will give us negative 3 times x squared minus 10x plus 25, and then plus 7. And I would recommend FOILing out or simplifying that squared of the binomial on the side if you struggle at all with this. I have no problem in you doing that. What do I mean by struggle at all with this? I mean you get the wrong answer sometimes. If you're getting the wrong answer, you're struggling. Now we have to multiply that negative 3 through. So we get negative 3x squared. We get negative 3 times negative 10x, which is positive 30x. We get negative 3 times 25, which is negative 75. And then we have plus 7. The negative 75 and the 7 can be combined together to give negative 68. I just need a little affirmation there, negative 68. So we end up with y is equal to negative 3x squared plus 30x minus 68. So let's be clear about what we're saying here in the warm-up. There's no real meaning yet behind why we're doing this, but what we're saying is this is the same as this. Better make sure I wrote that down correctly. Yeah. They're the same thing. They're in totally different forms. They have different appearances on them. They have different masks on them. They look different, but they mean the same thing. So if you look at this one on the right and you say, well, it's a parabola that opens down, you can look at the one on the left and say it's a parabola that opens down. I want you to notice something here, that this value of a is the number in front of the x squared. That will always be the case. So if I give you this function on the left and you don't know where it came from, you should still look at that leading coefficient, that 3 in front of the x squared, or the negative 3 rather, in front of the x squared, and go, oh, I don't know much about this parabola, but I know it opens down, and I know it's 3 times taller than x squared. If I give you this parabola, or the function for the parabola on the left, and you don't know where it came from, can you tell me where the vertex is? No. You can't. P and Q have been hidden from view here. There's a way to work backwards that we'll deal with later on in the unit. So, this thing that we've found is called the standard form. And I realize now when I type the notes out and I look at what I've typed, it might look to you like that first statement is saying y equals negative 3x minus 5 quantity squared is standard form. It's not. That's the vertex form. When we expand it out, it's the standard form. So this is the vertex form. The standard form was y equals negative 3x squared plus 30x minus 70, I've forgotten, 68? Thank you. Okay. And the standard form of a quadratic function can be written as y equals ax squared. It can be written as y equals ax squared plus bx plus c. So we'll get to the rest of that definition in a second. In our example up here, I hope everybody sees that a is negative 3, b is 30, and c is negative 68. They're the numbers in the quadratic function. All this other bit of business, this is like parsley on the fish. It doesn't really do much, but sometimes it's needed. They are real numbers, and a cannot be 0. Look, the reason why a can't be 0 is if a is 0, then this first term doesn't exist, and it's a linear function and not a quadratic function. Okay, that's all. All right, let's talk a bit about this standard form. And you know, if you like, I'm going to write these on the sideboard even though this won't appear on the video. You've got this vertex form, y equals negative 3, x minus 5 quantity squared plus 7. And we have the standard form, y is equal to negative 3x squared plus 30x minus 68. The standard form doesn't contain much information. If you look at this example of y equals negative 3x squared plus 30x minus 68, it contains next to no information about the graph. It really doesn't. It contains the fact that it opens upside down. It contains the fact that it's 3 times taller than x squared. It contains one other fact that you don't know about yet, but we will get to. Y equals negative 3 times x minus 5 quantity squared plus 7. The vertex form is rich with information. It's bleeding information. It's got the vertex is at 5, 7. The axis of symmetry is at x equals 5. Since it opens downward because a is negative, this number 7 is a maximum. And the maximum value of y of 7 happens when x is 5. This was all the stuff from the quiz, which I'll hand that back today too. Even though the standard form, which is the bottom one that I have written on the board, doesn't contain a lot of information, we still use it a lot. Okay. So let's take a look at the first example. For each quadratic function, identify the following. Which way does it open? What's the maximum or minimum value? What are the intercepts? What's the coordinates of the vertex? What's the equation of the axis of symmetry? And what are the domain and range? And I will tell you right now that other than pardon me, highlighting the wrong thing. I will tell you right now that other than this and this and this, there's nothing you know how to do yet from the standard form. We can do the direction of opening. It opens up because there's a number 2 in front of the x squared. So opens up. Which means there's going to be a minimum value. So I guess we kind of know there will be a minimum value, but we don't know what it's going to be. The y-intercept, we can find the y-intercept right now by putting 0 in for x. Let's look at what happens. Y-intercept, this is where x equals 0. We talked about this yesterday. That means y will be equal to 2 times x squared, which will be 0 squared, minus 8 times 0 plus 13, which is 0 minus 0 plus 13, which is 13. And I want you to think about this for a second. The y-intercept is always going to be this constant term. Because the x squared term contains x, so when you put 0 in for x, it disappears. The x term contains x, so when you put 0 in for x, it disappears. When I told you over here, looking at the sideboard, that this y equals negative 3x squared plus 30x minus 68 doesn't contain much information. I said it contains the fact that it opens down and is taller by a factor of 3 than x squared. It also tells you the y-intercept is negative 68. You can tell just by looking at it, the y-intercept is negative 68. Over here, the constant term is 13. What else did I say we can do? The domain. Well, the domain is any real number. Right? I'll put the domain up here. X is any real number. Now, I'm going to pause there for a second and tell you everything else you don't know how to do, we're going to do on the calculator. We're not going to do anything on paper here with regards to this other stuff. So we're going to graph this quadratic function on the calculator to answer all of the remaining questions. So we go to y equals and enter 2x squared minus 8x plus 13. And generally speaking, everybody, you want to go zoom standard first, okay? And be very patient here because some of you can get to a good picture quickly and others not. How many of you remember maybe last year trying to zoom in on a graph and it becomes frustrating? It can be very frustrating. So this is why I want us to go slow here and make sure that you follow along. Zoom standard, which is zoom 6, is where we always want to start. Now, it's not always going to be a great move, but in this case, we see some important features of the quadratic function. Now, take a look up here. I know that the y-intercept is up here at 13. So I have to change my window settings so I can see up to at least that far. I also know, everybody, when I go zoom standard, and I think we talked about this yesterday, it goes from negative 10 to 10 horizontally, and it goes from negative 10 to 10 vertically. Did I talk about that yesterday? I think so, I think in the seminar. So when I look at this, everything below here is a waste of pixels. There's no information given to me there. So I'm thinking my y should go from about 4 up to, I would probably go 16 because I want to see that y-intercept. Well, let's start with that then. I'm going to go to my window setting. I'm going to go to my window setting, and my minimum y, I said let's go from 4 up to 16. Okay, I can go graph and see now. Well, that's better, isn't it? But there is also a lot of wasted screen horizontally. This is all a waste. There's nothing there that's telling me anything. And this is all a waste. So if this was negative 10, maybe I should go from negative 3 to positive 6 for x. And that just shaves off the parts of the screen I don't want to see. Okay, so window, negative 3 to 6. Let's see if that... Oh, that's a much better graph. So let's use that graph to answer the remaining questions. First of all, let's get the x-intercepts out of the way. What are the x-intercepts? There aren't any, right? Because this parabola has a vertex above the x-axis and it opens up. So there's no x-intercepts. Now I'm going to ask a question. Look at what we've done. We've done this, and we've done domain, everything else. I want you to look at everything else. The key to everything else are the coordinates of the vertex, right? If we know where the vertex is, we can answer this question. So how do we find the vertex? On our calculator, you go to your calculate menu, which is second trace. And we know this graph opens up, so it has a minimum. We're going to choose the minimum option. And then it says left bound question mark. It is saying what is the left boundary of the minimum value of the function, which means even though we're talking about finding the y coordinate eventually, we have to be to the left of it and then to the right of it. So left means take your cursor, you see the little blinky guy there, take it and make sure it is somewhere to the left of that minimum, and then hit enter. Then it says, okay, well, you're not done. What is the right bound? That just means we're going to create a boundary on the right of that has to, well, it has to be to the right of it. So I'm going to scroll to the right and I hit enter. It doesn't matter how close you are. I mean, don't go really far away and don't try to go really close, but just kind of in the vicinity. And then it says guess. And we can guess if we want to, but it's not going to affect the ability of the calculator to come up with the answer. Just hit enter for a third time. Now we have a slight issue with the Texas Instruments family of calculators. It's saying the x coordinate of the minimum point is 2.000009. Mine says 9. Do any of yours say 9? Does yours will say 2.00 exactly? It has some different number, right? That's a glitch in the programming. Depending on your calculator, you might see different numbers there. Depending on your window settings, you might see different numbers. We have to know that it's 2,5. Okay? So the vertex is 2,5. We know everything now. Because if it's 2,5, the axis of symmetry will be x equals -2. I'll write the vertex up here. The axis of symmetry will be x equals 2. Let me repeat that without the screw up. If the vertex is at 2,5, the axis of symmetry is at x equals p. This is why it was so important to do well on that quiz yesterday, to understand that material. What are the coordinates of the vertex? Well, I guess I already have it. I'll rewrite it again. What can we say about the minimum value? The minimum is y equals 5 at x equals 2. What else are we, what am I missing here? That's it. I've got it all, don't I? Oh, the range. Thank you. It opens up and the minimum value is y, so the range would be y is greater than or equal to 5. But you find all of the information basically from the graph. Let's try another one. So we're going to enter -3x squared plus 6x plus 5. Zoom standard, always go back to the beginning and do something that I didn't do, but you should. Make sure you double check to see what you've typed is correct before you go zoom standard. And I don't know if you've encountered this with me yet, but sometimes for squared I'll just go xx. That means x squared. I don't know why I do that. Doesn't matter. Oh, zoom standard. See, this isn't good enough. Zoom standard. Okay, so can we see the vertex? Can we see all the intercepts? Yes, but I'm not comfortable with the wasted space on the left and the right. I would probably change my window settings to go from -3 to +5 for x. Just want a slightly rounded, more rounded picture. So let's do the intercepts first. Y-intercept. Well, we shouldn't need to really do anything for that. It's 5 because the constant term is 5. X-intercepts. I did this yesterday, I think, in the seminar. I don't know if you remember. We're going to go to the calculate menu again. Does anybody remember which of those options finds an x-intercept? It's the one called 0, because we're finding out where y is 0. That's what an x-intercept is. We're given this conundrum again, this problem, left boundary, right boundary. But we're not going to the left and the right of the maximum or minimum. We're going to the left and the right of the x-intercept. So at this stage of the game, everybody, when it says left boundary, if I am after this x-intercept, this is left of it, and this is right of it. So left means put your cursor someplace here to the left of it. Right is going to mean put your cursor someplace here, which is to the right of it. And again, you can scroll, or you can actually enter a value of x, negative 1.5. You even see a little arrow there. Do you see that little arrow up top? The little triangle, it's pointing there. That means it's going to be between there and wherever I put the other arrow. So now, right boundary, I'll put 1. Is the x-intercept between those two pointers? Yep. So when I hit enter again, it's going to find it. One of our x-intercepts is this number, approximately. We'll learn a lot more about those x-intercepts later, later, next week, maybe even the week after. And then I repeat the process on the other side. So left boundary is maybe around 2. Right boundary is maybe around 3. And again, if you don't want to eyeball it and enter them, you can scroll and then hit enter. The second x-intercept is about 2.63. So approximately negative 0.63. And I got that backwards. Approximately 2.63 and negative 0.63. The little dot above the equal sign means approximately. Now, we just got to work on the vertex now to answer everything. So the vertex, we go to our calculate menu. This time the parabola opens down, so we're talking about a maximum. Left means put your cursor to the left of it, or enter an x value that is to the left of the maximum. Then enter an x value, or scroll to and hit enter to a point that's to the right. Then hit enter a third time. So the vertex is at 1, 8. By the way, I hesitate in showing this to you, but it's not really that big of a deal. If you know the vertex is at 1, 8, then you know that this is the vertex form. Just give some thought to that. I told you earlier, with regards to this one I have on the whiteboard, that we will learn later how to go from standard form to vertex form. Well, I guess I've just shown you a way to cheat. Because A is negative 3. You can see it's negative 3 in both the question on the whiteboard and the one on the smartboard. And if the vertex is at 1, 8, P is 1 and 8 is Q. Which means, everybody, we're back at yesterday. You can tell me everything about this parabola. It opens up. No, it opens down. Opens down. There's a max of y equals 8 at x equals 1. I don't even think we need to look at the graph to understand this at this point in time. The vertex is at 1, 8. The domain is x is any real number. The range would be y is less than or equal to 8 because it opens down. Help a guy out here. What am I missing? Oh, axis of symmetry. The axis of symmetry is at x equals 1. Do I have everything? Domain, range, axis of symmetry, vertex, max, min. I think I got everything. Intercepts. All right, let's take a look at the next question. Now we start to get into word problems. We've got a couple of word problems we're going to be doing here in the next 25 minutes or so. A diver jumps from a 3-meter springboard with an initial vertical speed of 6.8 meters per second, and you're given an equation that can be used to find her height. All right? Just let's boil it down to what's important. Her height is equal to negative 4.9 t squared plus 6.8 t plus 3. That's her height above the water. And we're asked a whole boatload of questions. You are asked, I'm going to grab this, just give me a second. You are asked all of these things. Now I have a grid here because I might use it to explain a few things, but I don't know if I will. Let's graph the function, and I mean on our calculator. We're not going to make a table of values here. So we go to y equals negative 4.9 x squared plus 6.8x plus 3. Now we run into a problem, everybody, because you want to go zoom standard, but if it's a real application, zoom standard might let you down. I think it will be okay here. Yeah, it's good. But now I want to point something out to you about this graph. Does the graph exist in this quadrant? Does the graph exist in quadrant 3? No, it does not. And it doesn't exist in quadrant 2 because x is time and time can't be negative. So all of a sudden, since we have a new real world application, you can't just say the domain is any real number. Time, what's her time at negative 12 seconds? That doesn't make sense. So all of this, same with quadrant 2, all of this stuff needs to go. Does the graph exist in quadrant 4? Well, no, because she hits the water at some point in time, and she's no longer going to be obeying the law of gravity following this nice curve. She's going to probably start swimming away. Right? She'll hit the bottom, and then she'll come up and she'll swim away. And we don't show that. Right? In this graph, what would really happen is she would hit the water and slow down, and then she would swim to the top. So all of this needs to go. We only want to look in quadrant 1 because that's the only thing that's important. And now, think about this as well. This goes up to 10, but you can see she hits the water at just before 2 seconds. So this is a waste of space. And you can see approximately here that this is a waste of space. We're going to change our window settings to reflect that. Now, there's an exception here to this. I am going to tell you that you always want to leave some room below the x-axis, and you will see why in a second. So, first of all, for my x, I'm going to go from, we'll go from 0 to, let's say, 2.5 seconds. That ought to do it. Okay? I can show you what that's going to look like now. It's going to look like this. And in fact, you know what? I'm just going to leave it there. Can we shave off the negative y's? Yes, but I'm going to ask you not to, and I'll show you why now. We are going to answer every single question now from our calculator. What does the y-intercept represent? Well, the y-intercept is 3, right? The y-intercept is really the h-intercept, and it's where x is 0. So, we have a problem here. We're dealing with t and h as opposed to x and y. But what does the 3 meters represent? It represents the height that she jumps from. It's her height at the beginning. It's the height of the platform she dives from. I don't know if it says diving platform or diving board. I guess we can go back and look. Springboard. I hope you're not upset that I'm using platform instead of springboard. It's her initial height. What maximum height does she reach? I guess you need to find the vertex, don't you? So you go to your calculate menu, you choose maximum, scroll to the left of the maximum, hit enter, scroll to the right, hit enter a third time. Her maximum height is about 0.7. Nope. Her maximum height is about 5.4 meters. So for question C, I don't want to cram all this in. For question C, the maximum height is about 5.4 meters. When does she reach the maximum height? At 0.7 seconds. At the x-coordinate. So this is why I do have the graph here. I'm just going to put that this is 0.7, 5.4. That 0.7 is a time that she reaches the maximum height at. So at t equals 0.7 seconds. Do you see why I made a big deal about the maximum being a y value at x equals something? How long does it take before she hits the water? Well, we have to find this x-intercept, which means we have to go to our calculate menu and choose 0. Put our cursor to the left of that x-intercept. And then we have to put it to the right. And that's why I wanted some of the graph below so I could put my cursor to the right. And then hit enter. She's in the air for 1.7 seconds. 1.7 seconds after she leaves the springboard, she splashes down. What are the domain and range? The domain is not any real number. The domain is 0 seconds to 1.73 seconds. It's only the time that that graph describes her motion. The range is not h is less than 5.4 because there's a minimum. It's from 0 to 5.4. So this is the domain in between here. This is the range in between there. Again, if it's a real world application, you have to look at what these numbers mean. So the range is 0 is less than or equal to h, which is less than or equal to 5.4. And F, what is the height of the diver 0.6 seconds after leaving the board? There's a number of ways to do this. One of the ways, everybody, is you could take your calculator and put 0.6 seconds here and calculate the height. But there's a very quick way to do it. On these calculators, if you know x and want to find y, all you do is go trace enter the x coordinate, and then hit enter, and it will show you the y coordinate. It does that calculation for you. So 0.6 seconds after leaving the board, her height is 5.3 meters. Now, ultimately, everybody, this example is no different than the previous examples. It's just that it's an applied problem. When we get to the next example, things change drastically, okay? Any questions with this example? All right. We are going to, throughout this unit and the next unit, encounter a series of problems where we want to maximize or minimize something. This is called an optimization problem. Optimizing means make something as big as possible or as small as possible. For example, if I'm a business person, I want my profit to be maximized, yes? Makes sense? If I'm running a little hot dog stand on the beach to earn a few extra bucks, I want my costs to be minimized so I make more money. In this particular question, we've got a music festival, and we're going to rope off a rectangular area for stroller parking. And you have 160 meters of rope, and it's got to be shaped in a rectangle. So I want to ask you a question. Could I make a rectangle? Could I make a rectangle where this distance here is 65 meters and this is 15 meters? Can you do me a favor and figure out if that's going to be 160 meters of fencing, or not fencing, of rope? It is, right? Because we're going to have 65 and 65, that's 130. 15 and 15 is another 30, that's 160. Or you could say 65 plus 15 is 80, and then we have another 80. Could I make, instead of that, could I use the 100, and maybe I'll just say something before I do this. You understand that to maximize the area, you got to use all the rope? That's a smart move. Could I make it like this? Would that be 160 meters? Are they the same area? I mean, I think you can tell they're not, but what's the area up here? This would be 65 times 15. $975 square meters. Not bad. You can put a lot of strollers in there. 3 times 77 is 241. 231. Not as good, right? I hope you understand, though, that doesn't mean we should make this as big as possible, because if that length starts getting too big, the bottom length starts getting too small, and you won't get as much area either. This is the problem. What dimensions should we use to get a maximum area? And I understand that many of you will understand what the answer to the question is, but let's follow the steps here. A, write a quadratic function in standard form to represent the area of the stroller parking. So what we're going to do, and there are a number of ways that you can do this. I am going to choose to call this L and this W. And that means that our formula for area is length times width. And I'm going to try to teach this to you in as general a way as possible so that you can solve other similar problems. This is to be optimized. We always want to create an equation describing how to calculate the thing we want to be as big as possible or as small as possible. Okay? The only problem is this has too many variables. This is the best way I can explain it to you at this level, at this point in time. And the reason it has too many variables is we would like to be able to imagine a graph where we have area here and one other variable on the horizontal axis, because then you can find out where the max is. Right? The max is where the vertex of this is going to be. But you can't graph y if you have x and z as well. So we have to get rid of one of these variables. And we're going to get rid of one of the variables by writing 160 equals 2L plus 2W. And I would like everybody to just think about that for a second. Why 160 equals 2L plus 2W? Because we have 160 meters of rope, and we've got 2 lengths and 2 widths. And this is called, you may think this is maybe overcomplicating things, but I think language in math is important. This is an equation of constraint. It's an equation that we are handcuffed to. You cannot just pick any length and any width. They have to be tied together by that equation. So if you pick 1 meter for W, well, then you're going to have to get 79 meters for L. And I'm going to simplify it because I don't know if you realize this. We can divide the whole equation by 2. So our equation of constraint, I don't need this. Our equation of constraint is 80 equals L plus W. So which variable do you want to get rid of? First person who volunteers an answer will do that. What do you want to get rid of, the L or the W? I heard W. I don't know who said it, but somebody said W. Let's get rid of W. So let's rearrange our equation of constraint for W. And what that's going to allow us to do is take this and put it there. So A equals L times 80 minus L. And if we simplify it, we get 80L minus L squared. Is that a quadratic function? Yep. Does it open up or down? Careful. 8 is positive, but 8 is not the number in front of the squared term. Right? This is a little tricky. Not really tricky, but a little bit. If we write it in standard form, we put the squared term first, then the linear term, what I'm going to call the linear term. Because this coefficient is -1, it opens down. So there will be a maximum. And that maximum will be the maximum value of y, which is area. And that's what we're trying to find. Go ahead. Did I write? Oh, thank you. Thank you, Sasha. It's not 8, it's 80. Definitely. Okay. So we just, if you look at the rest of this question, what are the coordinates of the vertex? You know what? Let's not do C and D. I don't care about C and D. What are the coordinates of the vertex and what does it represent? We just have to graph it and find the coordinates of the vertex. Unfortunately, I don't think Zoom Standard is going to show us much, but let's find out. Well, no, I shouldn't say that. It will show us something. So we have -L squared plus 80L. So that's negative x squared. We put it in for y. Negative x squared plus 80x. Let's try zoom standard. How many of you have ever graphed something on your calculator and your calculator appears to freeze? And you see those dots in the top corner? Just to let you know, this happened to me a long time ago, many times, and I didn't know what happened, and I had to reset my calculator to clear it up. And it happened to a student one time, and I saw them do something, and it fixed it. Well, what happened here was when I hit graph, I hit enter right away, and that pauses the graphing. So if I hit enter again, it starts it again. Now, you can see the graph coming up through the origin, and then it must go up quite high. So I think what we should do, let's talk about and by the way, we're not going to do the next example today. I don't want to push it. Let's talk about the fact that I don't really care about any of this or any of this. This graph has a y-intercept of 0, and it goes up, and then it's going to come down. So it's kind of a guessing game here. Let's put in some information in our window setting. Let's go 0 to 10 to start off with. We're cutting off all the stuff to the left. And let's go 0 to something here, but we're going to have to go quite high, aren't we? So let me show you a trick on how we can decide how high to go. Go to your table. Set up your table to be on automatic. Maybe start at 1 and go up by 1. And if I go to my table, I can scroll down and I can track what's happening to y. It's going up to 500 and something. It's going up to 600, 700, 800, 900, 1,000, 1,200. Goes up past 1,500. And if I were smart right now, I would change my window setting or my table setting to go up by more than 1. So I might start at 39 and go up by 5. The point is, I'm already, let's just keep going here. I didn't start at 39. There it is. Do you see that it's starting to go down again? It's 1,200, 1,400, 15, 1,600, and then it's dropping again. The maximum is happening somewhere around 40, and the maximum is somewhere around 1,600. So in my window setting, I better go up to at least maybe 50, and for y go up to, I'm going to go 1,650, but you can play around with that number. This is the one area where you will get a little frustrated. If I go graph, all right, we're seeing it. Now I can find the maximum, and I can answer the question. So calc, max, put my cursor to the left of that peak, put my cursor to the right of that peak, and hit enter a third time. The question was, what are the coordinates of the vertex? Well, the coordinates of the vertex, this is my graph. You don't need to sketch it on paper. Here's my x-axis. Here's my y-axis. The coordinates of the vertex are 40, 1,600. That means the y-coordinate here is 1,600. The x-coordinate, which is width, is 40. So what does the vertex represent? It represents the fact that the maximum area you can get is 1,600 square meters. And it happens when the width is 40. And if the width is 40, I would like everybody to figure out the length. 40 as well, right? Is it any surprise that it's a square? How many of you suspected that, if you make one side too long, you lose area, but if you make that side too small, you lose area? The next example, which we're going to do on Monday, is a little bit different. It's not going to be a square. And there are lots of other variations of this problem. But some practice on page 174 and 175. This is dealing with standard forms of a quadratic function where what you are doing essentially is using your calculator to answer the questions.